I welcome you to this lecture of microscale transport process. The topic that we have been covering in the last class was dielectrophoresis, more precisely something called a DEP trap, where we were trying to relate this DEP force F DEP. We are trying to relate this F DEP and F drag. We are trying to see how this FDEP, the mod of FDEP and the mod of F drag, these two we are supposed to compare, and we are supposed to find out what should be the velocity of the fluid such that these particles can get trapped, right. And as a matter of fact, why are they getting trapped? I mean, let me repeat once again that you have a non-uniform electric field, that means is a planar electrode and an electrode which is a point electrode. We are simulating it by we are calling it a sphere, and we are saying that this is the dielectric particle. It could be a biological cell. And then we are saying that these electric field lines, since this is a non-uniform electric field, there are field lines traversing like this, and there is an intensity, there is a concentration of these field lines here. Okay. So, there is a concentration of these electric field. This place here, you have the highest density of electric field lines. So, you are expecting that here the electric if the electric field is stronger in this region, Now, then we said that this particle has an epsa particle, the dielectric constant, and the fluid had its own epsa fluid. Now, if epsa particle is more than epsa fluid, then the particle would be more polarized. That means, the charges on the surface, there would be more such charges on this particle on the surface here. And I pointed out that if you have a planar electrode, I mean just the way a capacitor works, if you have a planar electrode and if you had such cell there, what you expect is that the charges will align itself such that, or the particle itself will align itself such that these charges, they are consistent with the electric field. Okay. So, this alignment is always there. Now, to achieve that kind of alignment, these particle has to move either, I mean, if epsa particle is more than epsa fluid, then this particle has to move in this direction, because since field is here, the field is uniform. So, this alignment is possible, but here it continues to move towards this direction such that it satisfies that alignment criteria. So, that is why this particle will continue to move towards left if epsa particle is more than epsa fluid, and if it is other way, then the fluid would be moving towards this direction, or in other words, the particle will be pushed towards the right side. So, this is something which we are trying to bank on. This is something which is being utilized to trap a particle. So, this is what we mentioned here as DEP trap, and then we are trying to find out what is the FDEP and what is the F drag. What are the we are trying to find out the expressions. Now, F drag, we have already pointed out that F drag is very simple. F drag follows this Stokes law, and this F drag is simply written as you have this 6 F drag. This is written as 6 pi eta A into V, and this V is given for a microchannel, which is of rectangular channel, not a circular capillary. We have already given an expression for V in the last class. So, F drag part we understand, and we said that this F DEP has to be F DEP has to be greater than F drag, then only this is this DEP trap is going to trap the particle. Now, for the F DEP part, now we have pointed out this F DEP as something called P dot delta of E. This we already understood, and in the last class we are trying to find out some expression for P some expression for P and some expression for E, right. In the near the end of last class, we were trying to come up with these expression, and what we ended up with, you remember in the last class, if you go to the notes, what we ended up with is that if DEP at R0, that is equal to f DEP at R0, that is equal to, let me give the final expression you had, is 2 pi epsilon 1 epsilon 2 minus epsilon 1 divided by epsilon 2 plus 2 epsilon 1 a cube delta of E naught R naught whole square. Now, you remember what are these epsilon 2 epsilon 1, basically these are one epsilon is for the particle, the other epsilon is for the fluid, right. In the if you go back to the notes of the last class, we had equated, I remember we had equated the continuity in epsilon 1 del r phi 1 a theta, you remember, with epsilon 2 del r phi 2 a theta. That means, we are saying that at the surface of the particle, whatever is within the particle, whatever you are getting from the within the particle has to be equal to that outside the particle. So, that is there is a continuity, okay, continuity with the potential and continuity with the derivative of the potential. Now, so what we did in the last class, what was our definition for what is the 1 here? 1 is the case when r is greater than a, you remember, r is, this is for r is greater than a, and this is r less than a. So, that means, this epsilon 2 is basically the epsilon particle. Okay. So, this epsilon 2 is epsilon particle as per our old convention, and this epsilon 1 is epsilon fluid as per our old convention, right. So, this is what we have done in the last class, and this is something here we had an identity to work with, that we near the end of the last class we discussed about that identity, and you go back and check this identity yourself. So, this is the final expression that you end up with. Now, I said that, so this is now FDEP. Now, out of this here, what is left out now is you have to give an expression for this, and there is this sign. So, you have to take the derivative of it. So, you have to come up with an expression for this and take the derivative of it, and then you can put all of them together and come up with an expression for FDEP R0, which you can equate with F drag. Now, I said, how will you get this electric field? How will you find this out? Since it is a non-uniform electric field, in the last class I mentioned that this non-uniform electric field can be simulated by considering a mirror electrode. You remember, let me see if I can get that. Yeah, near the end of the last class, this is something which we have been talking about, is that here you have a point electrode and here you have a planar electrode. Now, instead of having a point electrode and planar electrode, if you take away the planar electrode and instead think of a mirror electrode at minus delta V. Here it was plus delta V and 0, but instead of that, if you put a plus delta V and here you put minus delta V as a mirror electrode, and then if you look at the electric field lines, you will find that they are very similar to the case where you have a planar electrode and a point electrode. So, by this understanding, you can have the definition of phi is given as this quantity r 0 by r delta V minus r 0 divided by r minus 2 h E z delta V. You can check it yourself that at r is equal to h E z, that means at r is equal to, that means at this position at z is equal to h, at z is equal to h, you can have phi as 0. You can put it here and you can see that this is the case. So, this is an expression for a non-uniform electric field that we are talking about, that is constituted by a planar electrode and a point electrode. So, with this phi, now what you need to do is you need to find out what is E. What is E? Because you are interested in what in the last slide what we had, if dep r 0 we have E here, and E you know is electric field is minus of del phi. Okay. So, if you have this as phi, now you take this and find out what is E. Now, so E at r would be equal to minus of del phi of r. This is the definition. Now, here you make an approximation. I give you the final result, and then you think about it, how we get in there. And the approximation here is something like this. What do we do here? Here what we are doing here is we are saying that the location that we are interested in to find the find the E, the location that we are interested in, that r is that position where we want to find out the E, or r is the position where we want to find out the f dep. We are saying that this position is much less than h. What does that mean? This position is, so that means this is much closer to the point electrode. What is r 0 here? R 0 is we have a sphere. This sphere has a radius r 0, that is what we are talking about. This sphere has a radius r 0, okay, and this dimension is h. So, the position that we are interested in from the center of this point electrode, the position that we are interested in is here, because if the particle has to be trapped, this particle will be trapped here around this location. So, this position of course is greater than r 0, that means it has to be outside the electrode, that is for certain, but this is much less than h. I mean, it is not here that you are trapping the particle, you are trapping the particle here. All right. So, this is an approximation you are making here, and if you make this approximation, look at this one here. If r is much less than h, then r would be much less than 2h. Then this term here, whether you have r or whether you do not have r, does not make much of a sense. So, it would be simply r 0 by 2h, r 0 divided by minus 2h, or this minus will cancel out, it would be plus r 0 by 2h. So, this quantity becomes constant. So, when you take a derivative with respect to position, then this term will not contribute, this term will become 0. So, these assumption will help taking out this term in the derivative. This term remains in the phi, but when you take a derivative of it, when you take a del of this, by this approximation you are not considering this term, because you are treating this as a constant. So, you are working with only the first term, and if you work with the first term, probably this is what you will end up with, minus sign cancels out. All right. So, if that is so, now you would be working with this E. So, this E has to go back there, and this E has to be put in there. So, what do you get in that case? What was the original expression for f dep? This is the expression for f dep, right? And here this E naught would be substituted. So, what you get finally is f dep at r, that is equal to 2 pi epsa 1 epsa 2 minus epsa 1 by epsa 2 plus 2 epsa 1 a cube del of this E naught square, that it was square, right. So, this has to be delta V square r naught square divided by r to the power 4. Okay. So, it would be del of this quantity. Del of this quantity here, these are constants, it will come out only r to the power 4. R to the power 4 means r to the power minus 4. So, when you take the derivative with respect to r, what do you get? You get r to the power minus 4. So, it would be r to the power minus 4 minus 1, right, and 4 will come out outside, minus 4 will come out. So, minus 4 divided by r to the power 5, that is what you will end up with. So, that minus 4 multiplied by 2, it would be minus 8. So, I am writing it as 8 pi epsilon 1 epsilon 2 minus epsilon 1 by epsilon 2 plus 2 epsilon 1 a cube r naught square has come out r to the power 5 and then delta v square and E r hat. So, this is the expression for FDEP. This is the expression for FDEP. Now, you need to find out what is FDEP max. FDEP max, this is you write that FDEP max is achieved when particle is close to spherical electrode that means this implies r when r is equal to r mean. And what is r mean? R mean would be equal to r 0 plus a. You cannot reduce r below this. Basically, r 0 you have to satisfy. R 0 is the radius of the electrode and a is the radius of the particle. Okay. So, you cannot go any close. I mean, you have to if the particle is attached to the electrode, then also you have to satisfy this requirement. So, this is the case. So, this is the r mean, and at r mean FDEP you can expect FDEP to be FDEP max. So, this FDEP max is equal to FDEP at r mean, okay, and that r mean if you put, then it would be equal to there is a way to handle this further. You can take a ratio of this. You can take a ratio of these two. Say let us call this, say, gamma is equal to r 0 divided by a. Okay, so this is basically the radius of the electrode divided by radius of the particle. Let us consider this as a characteristic for the system, characteristic constant for the system. So, in that case, r mean would be equal to 1 plus gamma into a. So, now if you put this instead of this r to the power 5, instead of r to the power 5 you write r mean to the power 5. So, if you want to put r mean to the power 5, what you get here is if you simplify this further, it would be 8 pi epsilon 2 minus epsilon 1 by epsilon 2 plus 2 epsilon 1 gamma to the power square by 1 plus gamma to the power 5 epsilon 1 into delta v square. All right. So, this is what is the final, this is the FDEP max that is possible. Okay. Now, if somebody wants to find out what should be the value of this FDEP drag at that point, at that location, in that case what he would do is we considered this to be an infinite parallel plate, right. There we have considered this velocity to be equal to 6 into 1 minus z by h into z by h into v 0. This is the velocity. This is that expression for the velocity, parabolic, what you call it, parabolic velocity profile in a rectangular channel. If it would have been a circular channel, you have that 2 v naught 1 minus r by capital R whole square. So, here you have 6 into 1 minus z by h into z by h v naught. So, this is the expression for velocity. Now, if you want to find out the velocity at this location, I would say velocity at r 0 plus a, what would that be? velocity at r0 plus a. With this expression, if we try to find out at r mean what is the velocity, at r mean the velocity would be, then if you simplify this further, you should be getting this as 6 into 1 minus 1 plus gamma into a by h into 1 plus gamma a by h into v naught. This is the expression that you get at r0 plus a. You can fiddle with it and see how you get this expression. So, this is the expression you get for the velocity at that location. This is the velocity at that location. At that location means at r mean. And what is r mean? R mean is basically r0 plus a. R0 is the radius of the electrode and a is the radius of the particle. So, that is the minimum r you can get. I mean, you cannot go any r below that. That is impossible. And you expect that at r mean the FDEP would be maximum. So, now this expression, this is approximated. This expression is approximated as 6 into. So, this is approximated as 6 into 1 plus gamma a by h into v 0. This is approximated as 6 into 1 plus gamma a by h v 0. So, this is the expression for v. Now, if we go back to that, so what is now f drag with all this understanding? What is f drag? F drag at r 0 plus a, that is at r mean location, that if we look at the mod of it, we are interested in the magnitude. This would be close to 6 pi eta a v x at r 0 plus a, and if you bring in those expressions for v that we discussed just now, you would be end up with 36 pi 1 plus gamma eta s square by h into v naught. So, this is the expression for f drag that you end up with, and this is what you are equating with FDEP max, which is at r mean. And what is that r mean? This is the expression FDEP r mean, right, 8 pi epsilon 2 minus epsilon 1. So, you are equating this with what is the expression? This is equated with 8 pi epsilon 2 minus epsilon 1 divided by epsilon 2 plus 2 epsilon 1 gamma square by 1 plus gamma to the power 5 epsilon 1 delta v square. So, this is coming from this is coming from that FDEP max, this side, and this is coming, the upper one is coming from f drag. Now, you equate these two and you will get a fair idea of what should be v naught. So, this is v naught. So, the expression for v naught would be something like this. This is the expression for v naught. You can call this a v naught max. Why v naught max? Because if v naught exceeds this value, then you know for sure that this particle will not be trapped, it will go out. So, this is the maximum v naught that you can permit for this system. All right, and to obtain trapping, of course, epsilon 1 has to be less than epsilon 2. Because you remember what were the epsilon 1 and epsilon 2 we defined just now? We said that epsilon 2 is epsilon particle, epsilon 1 is epsilon fluid, that is our convention, and particle has to be greater than the fluid. Particle epsilon has to be greater than the particle, then only there could be trapping. Okay. Now, So, this is an expression you get. This is the velocity, that is a maximum velocity that the fluid can have if somebody wants to trap a particle of these properties. That means, fluid has a property here, fluid has dielectric property given by epsilon 1, particle has a dielectric property which is given by epsilon 2. Gamma is the characteristic of the system, r 0 by what was the definition of gamma we used? We have used gamma as r 0 by a. That means, radius of that spherical electrode divided by the radius of the particle. So, that is what you have gamma. Each is the microchannel, that aperture, the distance between the two electrodes. Epsilon 1, you know, epsilon 1 is the dielectric property of the fluid. Delta V square, delta V is the applied voltage, and eta is the viscosity of the fluid, A is the radius of the particle. So, this is an expression you have. So, given these properties, you should have the V naught. This is the maximum V naught you can have. So, if you expect that particle to be trapped by the by this mechanism. Now, I said at the very outset that this entire analysis is based on DC field. Now, ideally it is used as an AC field, and in fact, if you look at some literature on this dielectrophoresis, they start with this AC field itself. Okay. Now, if you have an AC field, if you have an AC volt instead of DC volt, DC volt, then the advantages are no movement of isolated ions, d bilayer at the electrode is avoided. Now, this factor is referred as, there is a name to it. This you might have seen already. This factor we are carrying all the time, I mean right from the beginning, and this factor has a name. The name is this Clausius, Cl, let me write it clearly, Clausius Mossotti factor. Now, this factor, this, let me call it Cm factor for the brevity. I hope that's not that can be allowed here. Is this can depends on when you have an AC volt, this depends on driving frequency. Okay, because if you have an AC voltage, if you have an alternating voltage, then it has a frequency attached to it, and the Cm factor then depends on the driving frequency. So, what you will find is that if you this entire analysis will be repeated with these various places, you will have this driving frequency inbuilt. I mean, this entire analysis can be repeated for an AC electric field. Okay. So, you will see a lot of parameters, the framework remains same, but in many places you will find that driving frequency goes in, and most importantly the Cm factor depends on driving frequency. So, this offshoot is that this factor, it can even change sign, So, depending on what driving frequency you have for the AC field, this Cm factor can change sign, and you can see the repercussion of this changing sign. If the sign gets changed, that means a DEP force can be made attractive. DEP force can be made attractive or repulsive by choice of driving frequency. So, you get this flexibility. So, for these reasons this AC field would be more sought after than the DC field, but the analysis that we have done, the basic framework will remain same, only you will find that various constants we used there, these functionality with the driving frequency will go in there. You can check it out yourself. I am not covering this in this class because as such this derivation itself is quite complicated, but the framework remains same. So, that is more important, and I suggest if you are working in this field you should look into that aspect, because that is probably more important, and that is in some literature, I mean they start with that with an AC field how this derivation would be. So, that is how they have done. So, I guess this is all I have as far as the dielectrophoresis is concerned. So, what we are doing basically is we are picking up one by one various physicochemical processes that can have tremendous importance in micro scale. So, what we have done is, say we picked up electric double layer, then we talked about electroosmosis, electroosmotic flow, electroosmotic pump, then we have covered the electrophoresis. That is one way of differentiating a mixture of particles, and then you have this dielectrophoresis. This dielectrophoresis is well known for separating dead cells from live cells. Probably these properties that we are talking about, these dielectric properties, probably these dielectric properties they change in a major way if a cell undergoes this kind of transformation. So, these are so dielectrophoresis is I mean if you look at popular literature, this dielectrophoresis initially was meant for separating the dead. For example, you are trying to find out pathogen in a water sample, okay, and these water sample may contain several live cells and dead cells, and live cells are going to contribute to the, or not contribute, live cells would be the problem area. So, you want to know how many live cells are there and not just how many cells are there. So, that is how in popular talks dielectrophoresis was projected, that it is a remedy for separating those. So, these are some of the mechanisms that are important, and you these can I think you should know, one who is studying micro scale transport, these are the mechanisms which are unique, and of course, these dielectrophoresis, electroosmotic flow, these have been studied. These are in electrohydrodynamics, in those areas. These are very established topics, but when it comes to microchannel, and people found that this will have tremendous effect, this will have tremendous importance in micro scale transport, then these topics are kind of given a renewed thoughts, and probably what we are doing is something similar. With that, I mean I would be done with this electroosmotic flow and electric double layer and this dielectrophoresis. The next topic that I pick up now is more important for flow of gas through a microchannel, not a liquid. What we would be discussing, the next topic that I pick up is something called slip flow. That would be the next topic that I would be covering in microscale transport. So far we have been mostly focusing on the liquid and ions and ions getting pulled, but this is a different this is something called slip flow, and this slip flow, the importance of slip flow will be that there is one factor which I briefly mentioned this to you, that is given by this name, Knudsen number, right, this Knudsen number. And what is this Knudsen number? Knudsen number is basically lambda by L, where lambda is the mean free path of the molecules and L is the characteristic length, maybe the channel that the gas is, or the liquid or the gas is flowing, the dimension of that, the aperture of that channel. That is what the characteristic length is. So, this is the Knudsen number lambda by L. Now, what is the lambda? What is commonly what lambda you have for a liquid and what lambda you have for a gas? And we have done some scaling analysis to show that for a microchannel, when the L is of the order of 1 micrometer, okay, then the lambda that you have for a liquid, that is then this Knudsen number is not significant, whereas the lambda that you have for a gas, then this Knudsen number becomes important. Okay. And this Knudsen number defines whether you have a whether you have a slip flow or a or whether you have a slip flow or you do not consider slip flow. That means, you do not consider slip flow means you consider the no slip condition, right. So, in Navier-Stokes equation, when you solve this, one boundary condition we commonly employ is that at the wall there is no slip, right. So, here you can consider this to be a no slip depending on what is the value of Knudsen number. Let me point out some numbers here. Okay. The numbers are like this, that if Knudsen number is less or equal to 10 to the power minus 2, this implies continuum flow with no slip boundary condition. If Knudsen number is between 10 to the power minus 2 and 10 to the power minus 1, this implies continuum flow with slip boundary condition. If the Knudsen number is between 10 to the power minus 1 and 10, this implies transition flow, and commonly there is something called a Barnett equation that needs to be studied. Okay, that needs to be that is the regime that you have, and if Knudsen number is greater than 10, then you have free molecular flow. It is not a continuum mechanics at all. It would be free molecular flow means what you have in molecular dynamics, collision of molecules. Okay, and that is the regime you are in. So, completely continuum flow, Navier-Stokes, all these will be gone. So, if the Knudsen number is less or equal to 10 to the power minus 2, then only you will have this continuum flow with no slip boundary condition. Now, what we showed in the last class is that or what we showed previously is that lambda of nitrogen at 1 bar pressure is about 70 nanometer. Lambda of nitrogen at 1 bar pressure is 70 nanometer. Okay. So, you can calculate if you have 1 micrometer of the channel, then what would be the Knudsen number, and typically this 10 to the in this regime 10 to the power minus 1 and above, this regime is we what we will be doing in this class is this part you understand, continuum flow with no slip boundary condition you have studied time and again, fluid mechanics, transport phenomena everywhere. So, this I am not going to talk about, this part I am talking about continuum flow with slip boundary condition. Okay, that means here what you are doing is this is the ultimate free molecular flow, this is how you should be simulating it. But free molecular flow, you understand, how much computational effort would be gone just to simulate a event for so many seconds. Okay, for just tracking each and every molecule, it requires huge amount of computational effort. So, you cannot afford that. So, here you are somewhere in between, you are not discarding the continuum flow, but bringing in some aspects of free molecular flow, so that you can make a makeshift arrangement. So, this is their makeshift arrangement. This is probably even more towards the free molecular flow, this transition flow equation. This we are not this is a very important method, and you can go through this in your, I mean, you can take this as an assignment, but what in this class we will cover is only this continuum flow with slip boundary condition, and free molecular flow is something which comes under the domain of molecular dynamics. That is also equally important, but I will not be taking it up. We are kind of we are restricting ourselves to this particular one. All right. Now, you got to understand this, I mean, this continuum description. Continuum flow means you are using Navier-Stokes and heat and mass transfer equations. Now, continuum filled quantities, that would be considered in a continuum flow. So, we would be directly picking up this continuum flow with slip boundary condition, and what we would be discussing, probably we will spill into the next, this will spill into the next class, is something called a micro Couette flow. Micro Couette flow means this you have already studied when we first time when we studied these viscosity, definition of viscosity. The first thing what we studied is those two plates, right? One plate is fixed and the other plate is moving at a constant velocity u, okay, and this plate is fixed, right, and you have this separation between these two plates is h. Your system of coordinates is, this is x, this is y, and perpendicular to the paper it is z, and this is fixed. This is fixed and this is moving. This you have studied for the definition of viscosity, right. What we would do is, so what do you do generally? I mean, if you let me tell you, because we may not be able to complete this analysis here. What we would do in this case is we will solve the Navier-Stokes equation, which is very simple in this case, because you take so many assumptions. You take so many assumptions when you define viscosity. You remember the basic definition of viscosity. There you end up with this, the velocity would be linearly changing with distance. To come to that, you make certain assumption. Okay, and if you start with the Navier-Stokes equation and all the components are gone, and you will only end up with one term, and that is, so you get the velocity to be linearly changing with y and no variation in velocity in x or z direction. So, that is what you end up with. You are familiar with that part. So, that we will follow the Navier-Stokes equation. Only thing is, we will not use the boundary condition. The boundary, what was the boundary condition there? Boundary condition was that u is equal to 0 at the wall, and u is equal, the velocity is equal to 0 at the wall, and velocity is equal to u at this wall. That was the boundary condition. Instead of that, we will use a different boundary condition, and that boundary condition will arise from that boundary condition will involve the mean free path. That boundary condition, because you have to think about what happens at the boundary. You are assuming that these molecules, they are flowing and the molecule is coming to a standstill at the wall, but in case of a slip flow, what you will assume is that a molecule is coming, hitting the wall and bouncing off, and whatever momentum it carries, it will this momentum, there will be an interaction with the wall. If this wall is fixed, you have one situation. If this wall is moving, you have another situation, but this molecule will come and bounce back there, and whatever happens due to this, that would be taken into consideration. Okay. So, let me first write the Navier-Stokes equation, I mean the basic equation that we use, but before that we need to write down those assumptions first, what all assumptions we make to get into that equation. Maybe the right one would be to give the final expression. That would be better. I write the final expression and then say what all assumptions we have there. we write typically as these mu into del square u del y square, that is equal to 0. This is what you have. You have u in x direction. So, basically you have, I am coming back to this concept on this mu here. Ideally we have used eta in other in electrohydrodynamics or electrodynamics. There we have used eta, because there we are using something called a chemical potential, mu was involved. So, that is why for viscosity we are writing eta. Let me go back to this old system. So, this is how it is, mu into del square u del y square equal to 0. This is the equation that you basically solve. If you go back, if you remember, what we do is we start with the Navier-Stokes equation, but all the terms are gone. All the terms are gone because of certain assumptions. And what are those assumptions? Let us list those assumptions now. The assumptions here are incompressible flow, flow is steady and fully developed, number 3 is flow is homogeneous in z direction. So, the offshoot of these is these, or I should say the entire if we use this assumption, this implies there is translation invariance. This is a very translation invariance of the setup along x and z direction. This implies velocity field can only depend on y. What is y? This is the y. So, velocity field can only depend on y, and in x and z there is a translation invariance. Also, the driving force points to x direction. This implies only x component of velocity is non-zero. That is exactly we have here. U is the x component of velocity. X component, x is in this direction, x component of velocity. So, that is what you have. The other thing you are writing here is that a pressure, there is no presence of pressure on pressure gradient, only pressure present is hydrostatic pressure that is cancelled by the gravitational body force. So, in Navier-Stokes equation you have that delta, the del p term, and you have the body force term, right. So, they are gone because there is as such, I mean del p, and the only pressure that is present is the hydrostatic pressure, and so this is what you have. So, so you remember in the Navier-Stokes equation what all you have. Navier-Stokes equation you have Navier-Stokes equation what all you have? You have one v dot delta v term that is equal to 0 because of this reason. Okay. This is only pressure present. So, delta p and that body force term rho g, that is, they are cancelling out in Navier-Stokes equation. So, you are ending up with, and the other terms are all the velocity field only depends on y, and only x component of velocity is non-zero. So, what will you have? You will end up with this expression. All right. I mean, I hope this is clear. I mean, you can take it to check this. This has been done time and again. I mean, I am just revising. So, I think we should not be spending much time on this. So, in that case, if this is so, what would be the solution to this equation? U is equal to C1y plus C2, right. U is equal to C1y plus C2. And what you do when you have a no slip boundary condition, you say that at y is equal to 0, u is equal to 0, since it is a fixed wall, and at y is equal to h, u is equal to capital U, right. That is how you do it. And so, what you get, u is at y is equal to 0, u is equal to 0. So, automatically C2 cancels out. So, C2 becomes equal to 0, and at y is equal to h, u become u. So, C1 is basically nothing but capital U divided by h. So, what you get is u is equal to capital U into y by h, right, and that is why we said the velocity profile is linear, velocity is changing linearly. U is equal to, or you can write u by u is equal to y by h, dimensionless velocity is equal to dimensionless distance. So, velocity profile is linear, and that is what we have done for defining viscosity. You remember when if you go to any standard fluid mechanics book and look at the definition of viscosity, this is where they start with. We will continue with this exercise, we will use this expression, but we cannot write C2 is equal to 0 when you have a slip boundary condition. Okay. There we have to bring in that what we said, the molecule is coming to the wall and getting reflected, and this wall may have a velocity or may not have a velocity. So, how that so what happens? So, what we do is we come up with an expression for u in that case and compare, we keep these as a standard, this is the no slip condition, and where all we deviate in our understanding, where all we deviate from no slip. So, that is what we would be doing in the next class. We will start with this u is equal to C1y plus C2, but we will start imposing the different boundary condition. That is all I have for today's class. Thank you very much.